Professor Pandit, Vice Chancellor of ICT, Shri Pramod Khosla, Dr. Professor Thorat, distinguished personalities on the dais. I'm so happy that ICT got together with Shri Khosla to create this lecture. I'm grateful to you for inviting me to give this oration. By now, you have had pretty good dossiers of sustainability. And perhaps you would think nothing is left out. Maybe I'm going to disappoint you and tell you there is much more to sustainability than all the commentary that you have heard so far. First of all, sustainability is not an optional topic. It is an essential topic. That's why in the title I decided to use this word essentiality of sustainability. And my comments will be mostly concerned with chemical and allied industries, which in a way epitomizes the whole subject. I want to take you back that history of chemical industry has, without using this word sustainability, has practiced it. And I'll give you very simple examples to prove what I'm saying. You all know how H2S from sour gas fields used to be burned and thrown into atmosphere. That means you are throwing SO2 and some unburnt H2S. Today, all the sulfur that you use in the world is recovered sulfur. This is one of the most outstanding examples of sustainability, that something which was a liability, and by the way, emission of H2S was also responsible for closure of the LeBlanc soda ash process in 1850s, and a benign Solvay process for soda ash came. You can give many examples. You take sulfuric acid plant, where BSF was one of the leaders. We used to emit out 5,000 ppm of SO2. One could smell. Today, the emission levels are next to nothing, which means you have more sulfuric acid production. But take the example of burning any fuel which has sulfur. Most coals in the world have sulfur. Any of the petroleum fractions, unless it was a very sweet crude, has. As I said, most of the sulfur today is recovered sulfur from where? From the sour gas fields and from hydrodesulfurization activities, because we have put a kind of sulfur limit in diesel at below 50 ppm, approaching 5 ppm. All this liability has been converted into asset. So I am prompted to make a statement: there is nothing like a waste. Waste is a raw material with negative costs, and you should cash on it. So let's take this case of burning coal containing sulfur. And that SO2 is subjected to flue gas desulfurization. Shouldn't we be recovering that SO2? Chemical engineers have developed a technology of scrubbing SO2 selectively in presence of oxygen without any deterioration of the absorbent, and you can convert all that SO2 into sulfuric acid, which is very badly wanted, because sulfuric acid once upon a time used to be called king of chemicals. I'll now turn my attention that all of us need food. And because we need food, we will always have agriculture crops and the materials coming from agriculture. And I like to specifically single out bagasse from sugar factories. Remember, few years ago there was no cogen in sugar plants. Today most sugar plants have cogen. That was one very good example of sustainability. And many sugar companies today make more money by selling power. Some of them have 60 megawatts. Still bigger one can go up to 100. 20 is very common. And the modern technology of using bagasse in boilers will allow you to spare at least 30% of your bagasse for purpose other than burning in the sugar factory. And what is a bagasse? Bagasse is a mixture of cellulose, hemicellulose and lignin. And each one of them, and I want to take you back, packaging, polyethylene film, what was the packaging material before that? Cellophane. What was the most important thermoplastic film fiber? Cellulose acetate. Why are we not talking about going back? Because we can recover this high quality cellulose not only from bagasse, from other sources. We should go back. Cellulose acetate, very good thermoplastic, very good. In fact, even today, high quality dress material is from tricell, cellulose triacetate fiber, even today. But we are not talking about that. We talk about something with which we were not familiar, but the familiar ones are ignored because it's like saying, familiarity breeds contempt. I'm telling you, people are discovering in India that cars can run with pure alcohol. Would you know that up to 1956, North India, all the cars used to run on alcohol? Because there was no refinery in India, it used to be called power alcohol. And in late 50s, a great committee constituted by Government of India said the use of alcohol as a feedstock will be far more valuable than burning it as a fuel. Today you hear economics about how we are going to blend 10%, 20%, even more, run the car on alcohol, which we were doing before 1956 extensively in UP, Bihar, where alcohol was produced. Indian chemical industry, organic chemical industry started with alcohol as a feedstock. We were making acetic acid, acetone, polyethylene, synthetic rubber. The reason why I am mentioning this is, it is very good to say that I am using renewable raw material, but it has to face the market economics. All these plants are dead in India, practically dead. Why? Because they cannot compete with the feedstocks. Now, if we are saying we are going to go to electrical vehicles and all, which means the petroleum products for fuel purposes, their consumption will come down. And since so much was talked about, Reliance was the first refinery in India, with which I happen to have something to do, where major portion of, compared to any other refinery in India, and even in global context, was converted to petrochemical. So sustainability of petroleum refining is going to come through major portion, maybe sometime going up to 50% of the products going to petrochemicals rather than fuel. I mean, this is a kind of change that you will see. Now, it's not only bagasse coming from sugar. Of course, sugar cultivation itself is something, sugarcane is something requires reconsideration because it is a water guzzler, 12-month crop. We have still not introduced drip irrigation, consume water. And 70%, I'm going to go to this topic which is highly relevant from sustainability point of view, 70% of water is going in agriculture globally. Shouldn't the first charge be on human consumption? We can't go without water. So water is going to be one of the most critical factor in this whole game of sustainability. Without water, everything will collapse. Now, fortunately, we have 7,000 kilometers of the coastline. And thanks to developments in chemical engineering, hollow fibers, we have very good desalination. But we have arid zones in India. So water recycling is going to be absolutely critical for sustainability. Water guzzlers, whether rice crop or sugarcane, have to be examined very closely, and their sustainability must be checked in. Now, municipal water, take city of Bombay. Why should we be talking of any desalination when rainfall is so high and we can valorize the municipal wastewater into high quality water? Look at the example of Singapore. All the water comes from outside. 80% of the water consumed in Singapore is recycled, and they're wanting to approach 100%. Now, we had a demonstration unit in Chembur when Union Carbide was operational, and I am not seeing replication of that, which is pretty obvious for cities like Bombay. So, water recovery from municipal waste system is going to be essential. Now, when we are talking of fields, petroleum fields shrinking, gas fields shrinking, like we are seeing even our Bombay High production is coming down, and therefore you are looking for alternatives. But one of the items which has limited resources in the world is phosphate rock. And phosphorus is absolutely essential for crops. And whether you supply in the form of single superphosphate, ammonium phosphate, I prefer to even talk about potassium phosphate or potassium nitrate. In fact, in the context of sustainability, 6.5 million tons of potassium chloride being imported in India, should we be supplying KCl in the form of KCl, or shouldn't we be supplying in the form of KNO3 or potassium phosphate? It's very difficult to drill these thoughts into the mandarins of Delhi, And if you have something which is based on subsidy, you kill the innovation right away, because everything we want to depend only on so you find very few innovation in fertilizer industry simply because it doesn't pay. It's always good to talk, but it's very different. So water harvesting in arid zones, what can be? For example, if you are burning natural gas either for power generation or in furnaces in chemical industry, look at the amount of hydrogen that methane has. How much water is coming out of burning of 1 ton of methane? When you make this simple back of the envelope calculation, you will find that very considerable amount of water can be harvested. And this has been demonstrated in some units in Ankleshwar, which is water-stressed area, that exhaust gases coming out. After the conventional part, there is much more scope to harvest. One simple unit is recovering 20,000 liters a day after the primary recovery of water. So have you heard in thermal power stations based on natural gas that water is being harvested? It ought to be harvested. What else are we going to do? You are hearing a lot about capturing moisture from atmosphere in arid zones, in deserts. Thanks to massive developments in the field of adsorption in chemical engineering, we have wonderful adsorbents going for areas up to 3,000 square meters per gram, and you can harvest. So water recycling, water reclaiming is going to be absolutely crucial. I think it is the most important requirement for human beings and even for cattle and all. And then, of course, there are challenges. Can modern biology allow us to grow more crops from saline water or even seawater? If the nature can see coconut plantation on the coastal area, there is no reason that modern technology, biotechnology, will not allow us to grow crops on saline water, which will then save the fresh water which we want to earmark for the human consumption. So I like to lay a lot of emphasis. Now in this context, I want to turn my attention for a while. What will change this scenario dramatically in coming years is industrial biotechnology. And I explain to you why. Take an example, all these exhaust gases coming, let's say from blast furnace in a steel plant. There is already a demonstrated technology, and 2 units are operating, where these gases go through a fermenter and convert it into alcohol. Now you can twist this, take it to hydrocarbon. It's just like classic Fischer-Tropsch process, that anything which you can gasify into syngas, carbon monoxide plus hydrogen, instead of converting them only to fuel, Fischer-Tropsch today is operated in petrochemical mode, just as we talked about petroleum refineries operating in the petrochemical mode. Imagine if they had not operated in petrochemical mode, benzene, toluene, xylene wouldn't have been available, because coal tar is too meager a source to supply you benzene, toluene, xylene. So this is something very remarkable. that we will see just like this waste, imagine waste cassette. Now there is an extraordinary chemical engineering challenge, and my former collaborator J.B. Joshi has done some outstanding work, because you require extraordinarily high values of gas liquid mass transfer coefficient. Otherwise productivity will be very low. And we are talking of these mass transfer coefficient 50 times the number that we are originally conversant with. An extraordinary achievement has been. But what Francis Arnold, when got Nobel Prize, directed evolution. I have just read 2-3 days ago that industrial biotechnology has been used to make palm oil. There is already a semi-commercial unit for vanillin. Farnesene is being commercially manufactured. When you ferment to alcohol, you also emit a lot of carbon dioxide. But go back to Second War, when butadiene was required urgently to make synthetic rubber for the Allied forces to win the war. Butadiene was made by every conceivable process you could think of, but I want to single out 2,3 butylene glycol, which was made by fermentation. Look at the marvels of biotechnology today. I can twist the fermentation to give you 1,4-butanediol, which is commercial. Now there is also a biotechnology process to make 1,3-butanediol. So what industrial biotechnology can do, what nature does, we are not able to marvel the nature. If the nature can produce rubber, synthetic rubber, how much effort goes in making synthetic rubber. At ambient condition, you are getting rubber latex. At ambient condition, you are getting silk fiber. There is not a single fiber operation, synthetic fiber operation, which is anywhere near as benign as silk. Directly you are getting fiber. Here we have to have monomer, polymerization, this, and then you get your fiber or filament. So nature is going to be always the model. And I'm convinced. Now you take, for example, the intermediates. Our FDA has mandated that any drug which is racemic will not be approved unless you show the efficacy of the optically active isomers. Now, how do you get this optically? Because synthetic processes, only limited success has been. But fermentation, for example, the most famous drug for diabetes, sitagliptin, the basic intermediate is through biotechnologies. You get optically active molecule right away. Lipitor, atorvastatin, the intermediate required for that. Now, when you try to make by synthetic, it is not sustainable by any definition that you want to take for sustainability. But the expertise that you require, it's not like fermenting to get alcohol. I mean, you may get low yield. You have seen this in areas where there is prohibition, how they have instantaneous brew, keep ammonium chloride bricks and all. You can on spot produce alcohol. Alcohol is like a rogue. You can always, you won't go wrong. Your efficiency may be low, but you won't go wrong. But these require very sophisticated modeling. So in the whole business of sustainability, there are infinite challenges for academic scientists. They are not ordinary problems. They are very, very challenging problems. And history is replete that what was considered as a useless byproduct which you had to burn. I'll take you the classic example of diphenyl oxide, which came in phenol from chlorobenzene in Dow. And they then looked for uses for diphenyl oxide for heat transfer. Dow Therm was born. The name still continues. And the demand became so high that they had to on purpose make diphenyl oxide. So when you refer to sustainability, so if you have emissions from single superphosphate plant, can't this fluorosalicylic acid be used to make fluorine-based compounds instead of grappling with the disposal of that? So I repeat and say in a pedantic way, there is nothing like waste. Phosphogypsum, which is inevitable in the production of phosphoric acid by the most common process and the dominant process. phosphogypsum has been upgraded. First, of course, there was very complicated filtration problems, so you had to make seeming, otherwise 2 moles of water with calcium sulfate hemihydrate has to be made. And one of the most complicated filtration problem in earliest. People take filtration for granted, but even in pharma industry, filtration has posed many problems because you didn't crystallize properly. And when Professor Thorad had organized one seminar on crystallization, I made a reference that it looks deceptively simple, but I call it a case in molecular engineering, and that how you crystallize. If you don't crystallize well, you will not filter well. I must compliment you for the kind of job that you have done, and thanks to the materials of construction that are available from polymer industry, that you can have the nastiest molecule being handled now. But as I told you in my conversation with you, there is a new type of filtration now, apart from nanofiltration, where you are sieving out at molecular level. That molecular weight more than 250 you will be able to retain in a nano. Then there is a charge membrane which allows separation of divalent ions from monovalent ions. How sustainable these would be. And they are making a big impact in industry. Please believe me, in pharma and agro industry, nanofiltration is, of course, not like conventional filtration. Conventional filtration is indispensable in chemical industry. So you will always have a secure future, Yeah, you won't have any problem. So this water part I want to repeat again and again. And how cellulose can be upgraded. I refer to cellulose. You already know cellulose acetate. Then you also know CMC. Where is CMC going? Right from the ice cream which you adore to a lot of applications in oil well drilling and all. But the dominant part, and it's completely renewable in the sense, where would you go wrong? The main weight in the CMC is of cellulose. I refer to cellulose acetate, and you can have all the acetic acid from alcohol as long as you are allowed to compete. And not on the basis of government giving a fiat that alcohol will be at 60 rupees a liter. Ask the refinery if they are not forced to buy, will they buy? The guaranteed answer would be no. They are forced to do this, and under some specious arguments on which I don't want to commit. Now, renewable energy, Narayanan also made it. I'll elaborate this topic. Renewable energy from wind and solar is going to make a big impact on sustainability. Completely distributed ammonia plants. You may be doing that ammonia at 5 tons per day, 10 tons per day to serve the community. And since urea is very complicated, make ammonium bicarbonate. Carbon dioxide is always available. And why? Because, but all this is talked about as if it is like what we say, left-hand job. We are not doing the precise calculation that if you go for electrolytic hydrogen in a big way, do we have all the materials that go in the electrochemical set? Answer is no. We don't even have the membrane. They are all fluoropolymers. Where is cobalt in India? Zero. Where is nickel in India? In fact, I have been urging one source, uncommon source of nickel which people do not recognize and which I consider an interesting example of sustainability is pet coke gasification. Pet coke contains a lot of nickel and vanadium. You will be surprised that 20 million tons of pet coke being gasified can give you several thousand tons of nickel. Would you believe that? It is. So, when you gasify pet coke, now when you put pet coke in cement kiln, all gone. Sulfur gone. Metals gone. Whereas if you do gasification, and there are benign gasification processes. For example, I headed a committee to do underground gasification in Mehsana area. Underground coal gasification. We have coal there. Most people do not know we have proven reserves of 60 billion tons of coal which cannot be mined because depth of more than a kilometer. and seams are thin. But we can do underground coal gasification. It is a very pet topic, but nothing gets done. I mean, we do nibblings and all. We are not putting our heart, because this is completely sustainable, because unlike coal burning, in fact, that is a very serious problem in terms of sustainability. We are going to generate 1 million ton per day of ash. How much of it can be used in cement? How much more can be used for other purposes? Can we make zeolites from the coal ash? Yes, there is a strong possibility. It has alumina, it has silica. Just as rice straw has become a very great source of silica. In fact, there are already plants in the world making precipitated silica from rice husk being burned, and that's the only crop where silica content is so high. And therefore, you can valorize, and in fact, a lot of carbon black is proposed to be replaced by precipitate silica, because far more benign. And that reminds me that one of the big things about sustainability is tires. So earlier, shredded tires were allowed to be used because cement kiln was a killer. Put anything, it will get. But they are not allowing, because some nasty fumes come out and you are not able to take care. So there is ban in many countries for burning shredded tires. So now, and very interesting, now all these have strong links with chemistry and chemical engineering. All this sustainability in the chemical industry has a lot to do with high-class chemistry and very demanding chemical, not ordinary chemical engineering. I mean, I always say real problems are far more challenging than fictitious problems, It is very important I made this reference to underground coal gasification for that purpose. I'll turn my attention. You often hear about solvents being produced. Now, if I were to tell you that 100,000 tons per annum of methylene chloride is consumed in pharma industry, then you will ponder where is this blessed material going? So we need to be very cautious on recovery of solvents to make it sustainable. Technology provides you through various channels these recoveries. APIs in pharma industry, some of them 1 kilo would give you 10 kilos of unwanted material. 5 is very common. Should you be treated them as a waste, or they are raw materials with negative cost? I dare tell you that those who attempted, and I have had some, and we made crores and crores of rupees only recovering chemicals from so-called waste streams. So I again repeat in a pedantic way to tell you there is nothing like waste. It's a valuable thing. You have to apply, scratch your head and see what else can you do. Many such examples I can keep on giving you. Maybe burn coal. We are now using fluidized bed gasifiers. Number of locations in India. Good success because high ash coal in India, 35-40% ash. But why are we not doing in 2 stages? Even if 50% of the volatile matter, if the typical volatile matter in coal is 25-30%, and half of it I recover, and I am burning, let us say, 1 billion ton, how much of liquid products I will be producing? And petroleum refining gives me all the technology to convert them into subsequent valuable product, including fuels or chemicals. We are not doing that. Why we are not doing that? Please don't ask me. I have tried to impress upon that we should do this fluidized bed gasification of coal in 2 stages, recover at least 50% of the volatile matter. Now, the examples of the kind that I want to quote to you in addition are, I already referred to reclaiming sewage, but I want to take it further. What is left out? I mentioned to you in the very beginning that phosphate rock deposits are limited, and there is no substitute for phosphatic fertilizers. We have to look for new sources. And one such uncommon source is what is left after you do sewage treatment. because whatever phosphorus has gone from human consumption, it is in that. And there are now at least 2 proven units in Holland where you recover phosphatic fertilizer from this. It's an ingenuity of how magnesium, ammonium phosphate or something similar that can be recovered. We have yet to see that kind of attempt in India. Even in big cities, look at amount of material that you would get in Bombay or in Calcutta and all. This can be a completely uncommon source of phosphorus, valorizing something which might be a bit of a nuisance. The electrolytic hydrogen or wind. Now let's take, we are talking about it as if it is easy, you can do it tomorrow. It's not so. It's hopelessly complicated. Let me tell you both and explain to you. You put all your numbers into generation of electrolytic hydrogen on the scale that we are envisaging. Find out whether we can get the materials. Where from will you get the materials? We have 0 cobalt. We have no nickel. You talk of batteries for storage. We have no lithium. Cobalt is controlled by a country which is perpetually at civil war, erstwhile Congo. So we are not answering that part that you want to go for hydrogen economy. How will you support that hydrogen economy? Similarly, you talk of wind. Fortunately, because we have a long coastline, offshore installations, what can we do in terms of more sustainability? If we have 80-meter wing, go to 100, you see the jump in power generation. And you go to 200 meters, you will be surprised the extra power, quantum jump. Hang on. Now they have limited life. So there is a recent treatise of how many tons would be, because life is no more than 20 years. The wings that have come out already, and what will come out in 5 years' time from now, it is in thousands of tons. How are you going to dispose them? So you want recycling, just as we talked about recycling of polymers. And PET is an extraordinary example of recycling, but something similar can be done for nylon, something similar can be done for polycarbonate. We are facing problems in polypropylene. But given all the attention that we wish to give, we'll solve that problem. Even the multi-layer polyethylene film problem. After all, what is polyethylene? Polyethylene is glorified wax. And we were doing wax cracking earlier to make olefins. So you convert this into oil, just like from the biomass you get bio-oil, and bio-oil can be valorized. Pyrolysis of all this polymeric waste is already commercial. And it is being blended with naphtha for naphtha cracking. Now, naphtha cracking, there are only few operations in chemical industry which are non-catalytic. And the prime one is cracking of naphtha or ethane. To make them more sustainable, it will be necessary to develop catalytic processes. There was a reference made that how burning the fuel in the furnaces, because they are highly endothermic reactions, that how you can do electrical heating, and BSF has a large pilot facility in collaboration with 1 or 2 other companies. And this will make a big difference. And there is a lot of reference to CO2. I referred to you about off gases being taken to fermentation. And people were talking about algae. And now many treatises have come that if purely from economic point of view, at least as a source of fuel, algae will fail. But if you get the nutritional materials out of it, there may be some benefit. So catalytic processes, which non-catalytic processes are strong candidates to be converted into catalytic processes to make them more sustainable. And this electrolytic hydrogen, very uncommonly you talk about oxygen utilization. And what is the real challenge in coming years? Can I use that oxygen also for a conversion process? Remember, the electrochemical processes are going to renaissance because of distributed power and sophisticated specialty chemicals can be made. Anything which requires oxidation and reduction can be done electrochemically. So you will see in coming years, smaller places, people going for electrochemical processes. And the intriguing part here is, can you take that hydrogen and oxygen and, although number of papers have come, convert them to hydrogen peroxide? Some pilot facilities are there. It will be an extraordinary achievement. Just as in sustainability, when ethylene oxide was all made by chlorohydrin process and got replaced by oxidation process, propylene oxide today is from propylene and hydrogen peroxide. Chlorohydrin is gone. They are the very sustainable processes today. And many such, but all phenol used to be made by benzene sulfonation, alkali fusion, chlorination, high pressure, all done by cumin process. So sustainability has been a part. It's fashionable, like green chemistry was integral part of, but it's fashionable to talk in terms of sustainability in chemical industry, green, and of course it makes sense. Look what happened in the coating industry, how it became more sustainable. Go back, elderly person, go back to earlier days in your life. Whenever painting was done, the smell persisted for a long time. Emulsion paints made extraordinary difference. Wonders of acrylic esters. And acrylic acid today is made by a benign process, not by Reppe chemistry using acetylene and all. When Reppe acetylene-based chemistry got replaced by ethylene-based chemistry, it was a great example of sustainability. Or when very high-pressure processes were replaced, like acetic acid, by carbonylation of methanol from 600 bar coming back to 40 bar, they were sustainable. So there have been examples all along. But coating industry, in terms of, you have often heard now, we are a very dusty country, you know. You always get these numbers even on television screen, the particulate matter. So you need dust-proof coatings. But now we are talking about heat reflective, because we are a hot country. You cut down the load on your cooling arrangement, you want heat reflective coatings. They are already in the market, not yet in India. Although dust one part has been copied from whatever is done, not originally developed in India. Many of these things are strong candidates to be developed in India. I can go on and on because examples are unlimited. Scope is unlimited. And I like to conclude by saying, you know, sustainable is attainable. And that chemistry and chemical engineering will play a pivotal role. So hooray to them. Thank you.